have it recorded, actually. Okay, so let's, it's a great pleasure. I actually want to take advantage of such an occasion. So I prepared very carefully for weeks, adding ideas as time goes past by. There will be too much information in there. So just pay attention to the message that interests you, that's intriguing to you. But I'm sure you will be able to pick up all the fundamental information that I'm going to give you. So let's start. I know I was given 2 hours, which is obviously too long in general. But the advantage of that is I can absolutely completely relax. There's no pressure to rush. But it means so much information. There's no way I can count on you to absorb them properly. So just pay attention to the part that interests you. And you will not miss the basic points there. Again, this talk will be, to properly treat this subject, you would have to take 2 3-credit courses. So can you imagine in 2 hours? At least the main message is that much. So speaking of today, so we're talking about protein structures today for Nobel Prize in Chemistry. Let's talk about polymer structures, okay? Let me just motivate you why this is such an exciting subject. Figuring out why we have sufficient mechanical properties. Because all of our polymers, largely, almost everything, we use it because it gives us adequate mechanical properties. But when you make a new polymer, when you recycle, when you do whatever, your next polymer may not be adequate enough mechanically. Therefore, you must figure out what is necessary to have proper mechanical properties. So I think that's enough to say we care about mechanics because that's the whole subject of polymer science, to me. And the nasty thing about it is all your polymers that you use, several hundred billion pounds you use, they are all high molecular weight. And you will soon perhaps appreciate why they need to be high molecular weight. But when they're high molecular weight, it's very nasty to process. And that gives rise to the question of rheology, how to process it, right? The challenge in processing. At the end of the day, you improve the material in terms of strength, resistance to fracture. It goes back to the question of looking at the polymer structure, what can I do to correlate, right, to improve. So these are movies, I don't know, you paid attention or not, it doesn't matter. This just shows the kind of scale, several stories high, to produce polyethylene films that you use in your shopping bag, whatever else. And this is related to processing, and it shows as you extrude, nasty things can go on, and something like this. At the end of the day, this turns out to be a very difficult subject for a very, very long time, because it appears whatever nasty things you are dealing with has to do with molecular weight being high, the system being so-called highly entangled, and they are just a mess. And whatever is happening at the nanoscales, chain level, is responsible for what you observe at the microscopic level. The bridging of 6th order magnitude is a tremendous challenge to make. And the only way you can make it in principle is through theory, actually. So you better have reliable theory in that sense. Okay, so you don't know, if you don't know how old I am, about 35 years ago, I started to go to Epia's March meeting for the first time. I didn't, unlike many of my students, as a student, I was never sent to see it. So as a young faculty, I went there and see these programs. These are standard topics in polymer physics happening at the so-called DPoly, division of high polymer physics at the American Physical Society. And this topic struck my attention because at that time the subject is still relatively new. This book was just written, just published, 1990. Just to make sure the subject still thrives and survived. So I subsequently attend several of these meetings. They all have this topic of so-called polymer rheology or mechanics in it. So just to make sure this subject is still alive, this list actually is coming from to be next year March meeting list. So you see these topics are constant there for 35 years. So today I'm going to actually focus on talking about all these three subjects in the red box. And going back, so I learned as a young assistant professor, oh, there are a few key topics in polymer physics that we need to work on. One is polymer crystallization, another is polymer rheology, and another yet is polymer glasses. The nature of glass transition, aging. Nowadays, you have so-called thin film, having depressed TG, and so on and so forth. And of course, it turns out all of these subjects is relevant because of the difficulty to understand this effect called entanglement, the uncrossability. So today, you can raise the questions that was there 30 years ago. And by the way, recently I discovered we should add another standard topic to that March meeting, which is mechanics and fracture mechanics of polymers. I would insist we should add this topic onto it. So in each case, there are fundamental questions 20 years ago we asked, and we still ask today. So for crystallization, there's a question of what crystallization does to entanglement. For rheology, there's a question of how entanglement, which is this uncrossability, is responding to large deformation. And then another yet, how come the glass can flow? What on earth is going on? How come the glass can flow? So I have a few samples here, and I will make some demonstrations subsequently. And lastly, which is kind of what I insist on putting in, have we figured out why polymers are not strong, or not stronger and tougher? So these are foundational questions at the core of the main subject that have been around for 35 years. We start to make some progress. That's why I'm talking about it, right? And at the end of the day, to address these topics is to address the question of so-called structural property relationship. It turns out it's sufficiently difficult to figure out what structure gives you better properties. Once you do know that, then there's a question whether you can manipulate the structure through processing, right? So it's really a three-component chain, I would call it. I have been teaching polymer physics for 35 years, something like that. So I'm obligated to show what's available on your bookshelf in terms of polymer physics. These three books says nothing about rheology, says nothing about mechanical behavior. Why? Well, the author doesn't know the subject. Why would I write about it? I'm with them. You should not write something that you don't know about. You're not a first-hand researcher on it. The next subject, two books have a tiny chapter on mechanical behaviors. Similarly, a tiny chapter on mechanical behavior. So these are 7 books on polymer physics. Nearly completely ignore the question of mechanics, which I said should be at the center. It's a centerpiece of polymer physics, yet it was not that. Why? Well, we probably will find out soon why. In fact, that's intriguing enough question. As a consequence, the number of people working on the subject of mechanical behavior polymers is a very small fraction of all. Amazing. Going beyond textbooks, here are 6 books on supposedly covering the topics of mechanical behavior and rheological behavior polymers. 6 books. I will, as I move to the different topic, I will mention some feature or some information statements in each book, most of it. But this summarizes our knowledge up to, let's say, a decade ago. Okay, they are monographs. They are the state of art, and in today's, you will see, we are making major updates on them, and that major updates is going to happen through the 2 books, one published, one I'm writing. So let's start. I want this to be a kind of informal, and certainly I want to have it in the spirit of a class teaching. So let me share with you the most elementary piece of polymer science knowledge that you will acquire if you start to take next semester for your new student from my polymer physics 2. But for those who anxious to know the basics, and by the way, the basics are missing in polymer physics textbooks. So let me say, let me indicate what I mean. So I'm not going to go into details of polymer. Everyone knows it's just a Gaussian chain I can draw, and it becomes flexible. To describe that flexibility, you use so-called cone lengths, which, by the way, all polymers are backbone are carbon-carbon bonds, and consequently, the side group is not affecting this rigidity very much. So you end up having a cone length generally 1 nanometer for most polymer. But the second parameter, I call the second length scale in the problem describing polymer structure, is called packing length P. It's absent in Rubinstein's textbook. It's absent in perhaps, I didn't check all 7 books. It's probably absent in all 7 books. This P, without me introducing all the details, it just represents how thick your chain is. Okay, that's it. So it turns out we can tabulate this. For polyethylene, that P is 1.7 angstroms. For polystyrene, is 4 angstroms, because it has a benzene ring on the polystyrene. So it's just thicker, pictorially and geometrically thicker. That's it. The rest is you can take dozens of polymer and you see that the variation in cone length is very little, but in packing length is very significant. This is almost, of course, I want to emphasize, this 2-length scale is single chain property, okay? It's just one chain has this property, thickness and flexibility. Okay. Of course, this I just find it's necessary to say. So once you have a polymer, you wonder how mechanics can be described. It's described by stiffness. It's described by whether when you stretch, it breaks or not. For example, this sample I bring to you, it doesn't break. So one way of stretching, I cannot demonstrate that. I just show it doesn't, when it bends, it doesn't break. So that's the blue. It's ductile. Whereas the brittle one is this one, like say polystyrene. This is a polystyrene sheet. It breaks. That's it. Your dear plastics behave in one of the 2 ways. That's it. As you stretch, which I demonstrate through bending. And nomenclature, you may call that, let's fix that nomenclature. So you may call that nominal strength. Yeah, no, it's just apparent strength by, with that this material can exhibit. Goes back to my question, hey, is this strong enough, right? That's the kind of question we need to answer. And when it's not ductile, it just yields. In the sense we call this start to flow to become plastic. Okay, this is sort of common sense kind of thing. So the rest is what I emphasize again. So if you can figure out what structure give you better properties, you may use rheology to improve that structure. And we will show several examples of how that can be achieved and how industry have been doing that, by the way, right? So for those, again, who are relatively new to polymer science, there are 3 forms of polymers, as far as we generally say. Nowadays, Vitromer is fashionable, so I may bring that as in the category of thermoset. In fact, there are only just 2 classes, cross-linking them or not cross-linking them. Okay, that's it. So if you just making a finer classification, you may call this thermosets. Thermosets is a pretty major part of the whole thing. But plastics is, of course, is the dominant one, and then elastomers, of course, you use in tire, which is a very essential component of aspect of applications, right? So you can look at textbook, you can find out if you just make a little small deformation, how it behaves. You need to connect molecular level information to how rigid it is, and so on and so forth. And then when you have large deformation, all kinds of things can happen. So for example, this is a piece of elastomer, and I can stretch until I break it, rupture it, so-called. Man, physicists, polymer physicists, mostly throughout history, shy away from that subject of the sample breaking. This is too complicated a problem. Let alone you want to understand it at the molecular level, which presumably is what we want to do. So in any case, bridging all these different materials, the commonality is the fact that they fail and they fracture. So is there a uniform framework for that or not? So at the end of the day, they were just this kind of question. You don't need a lot of preparation to appreciate that these questions are significant, important to answer, right? Polystyrene, I just showed you, is brittle. Why? Because I just showed you this polycarbonate is not brittle. So what's going on, right? Secondly, how does I just showed you this elastomer? How does the elastomer rupture? You know, what happened to it? You may tease yourself, say, "Gee, should I blame that your covalent bonds are not strong enough?" Or what happened? Do you always have transition or not? Right. So these are the questions. So going back to the fundamental questions, it pays to ask the question why you squeeze your polymer melt state out, why it gives this ugly extrudate, right? And if you have a glossy polymers, this is polystyrene. So indeed it's brittle. Why it's brittle? Well, the very same polystyrene, if you do it in compression, it's like a piece of honey. It doesn't break at all. Gee, what's going on? It's the same polymer. And then, of course, there's the question of fracture. So this is an example of showing how a piece of PMMA fractures in front of your eyes. So these are the questions. So let me go one by one and show you how we could, at least at the conceptual level, start to handle all these questions. And to remind you, your polymer exists in the form of liquid to be processed when temperature is high enough. So you don't have crystallization, you're way above TG. But as soon as you cool down, which is what your final product will be, you have solidified your system either through crystallization, like an example of it, or because you have glass transition, or you cross-linked it. So at the end of the day, all we use typically are solids. The only place you use polymer in liquid state is you add some additives in your engine oil, for example, in a few places, very few places, in doing so-called turbulence reduction or things like that. The reason I have to review rheology is it turns out if you have no understanding of this rheology, there's no way you can make progress on the subsequent subject of why polymer is brittle and how strong you can make polymer to be. So let me just quickly say something about rheology. There's, I can turn this into a philosophy class again. I can talk about the history of this field. The short, I will probably not do that because you may not, without a large background, you may not know why I'm doing all this. But nevertheless, this is a book published in 2018. It admits that the problem of looking at the processing related to very large deformation kind of problem, we don't have a good theory, a good understanding of it. And then it's published in 2018. After my book, they cited the books. My book was not among them. And in fact, the leading author in the same year when he published the book, all of a sudden wrote me an email saying, "Hey, Shijing, let's stop arguing. Let me see, where is your publication? Let me study them." Isn't that too late? I'm just joking. So in any case, this understanding, so just a quick sense of, I mean, for Puru, probably he didn't even see this basic phenomenology. So basically, you try to understand processing behavior, which is a nasty problem, can be a nasty problem. People spend millions and millions of dollars to make it better, faster, and so on and so forth, problem-free. And the way to mimic it is simply just put it in a so-called shear cell, and then you try to shear the sample and see what happens. And we were crazy enough at that time to realize something might happen quite dramatically. Keep in mind, this is only 1 millimeter, so it turns out you need to magnify, you can do peaking, you need to use a magnifying lens, objective lens, to see over a millimeter what happens. And this is what happened at 1 millimeter level. And you find by shining light, by tracking, using particle track, you find the shear is not homogeneous. See, it breaks up. And this is a steady state, that it doesn't recover. So this top, that's textbook assumption going out of the window. We pray to God and assume the scenario of pure homogeneous shear occurs, but it does not. We assume so because it's 1 millimeter, we never visualized before. So there was an effort to visualize it, and you find it's not. And in fact, the more dramatic, conceptually important point, I remember Susie asked me that question, is you make a step shear, or in this case, you make a step stretch. By that time, we had the sufficient understanding. We know if you just hold it, it will break. You can predict it. Because what you deformed was too much already. When you stop, there is no way the cohesion can be preserved. And the breakup is inhomogeneous or localized. It's not surprising. In the filament case, it's localized. But even in the shear, they just choose a plane and to break up. So which is very dramatic. And again, keep in mind, this is a millimeter. You see that between them, they start to break up. This is earth-shaking because prior to this moment, we always perceive after deformation, there will be quiescent. There should be no visible macroscopic motion. That's the perception for many, many decades. But if things start to break up upon scission, then you see this possibility. So this was all what? Nearly 20 years ago, the understanding. So what this movies that you see, that I see, led us to realize is perhaps perhaps it tells us not only the structure, but how the structure is breaking apart. So the way we'll perceive it to break apart is this red chain being stretched. Eventually, you build too much force in that red chain. The blue chain cannot hold it. So this thing will start to disengage with each other, or disentangle, so-called. And the best way is I can take a piece of rubber band. My hands are the blue chains, and the rubber band being the red chain. It ends up eventually reach a so-called point of force imbalance. There's just no way you can keep hold of that much deformation of the chain. So at the chain level, it appears that's what happens. And moving on, we of course are very concerned about trying to understand what processing happens. We use the same technique. We impregnate a sample with some light refracting particles, and this scale again is millimeter level. So you just look at how the sample rushes into the die and being extruded, and you find nasty internal failure. As a piece of melt, a so-called piece of liquid. So liquid can break up in a fashion, in a manner that's like a solid. This is almost new to the polymer community. And so just nasty things can happen. Again, we're just looking at this part of the sample. The yellow box is that what this movie is. So it goes a little slip and then fails all over the place. And that's what produces this nasty exudate, it turns out. And that's related to all the processing problems you have. Yeah. These are 10 micron light reflecting particles. The only purpose of having them is to be able to see. So it allows you to see how the deformation field is changing in real time.
But they're not real particles? I'm confused. Are they real particles?
They are particles, yeah. So you just impregnate 100 ppm. Very small amount. Right. So the particles are much bigger than molecules. They're just sitting there as a suspended particle. So it reflects the local strand or speed of the fluid.
So polymers are not entangled?
Polymers are highly entangled, otherwise this could not happen.
Yes, so these particles would not be the whole polymer.
Actually, I can try to get fancy if you want to use this so everyone can hear you.
Oh, I'm sorry. So I'm just trying to understand.
Closer, yeah, just closer. Yeah.
What I'm looking at there.
So a few hundred ppm of particles is added to the sample that are light reflecting. And then I shine a laser.
Okay.
So the joke was the experiment takes a $100,000 machine, whereas this ability is $300. Just the presentation laser pointer and a surveillance camera with the objective lens. Yeah, so it's just, in fact, this got the Jin involved. Okay, so I don't have time for it. And they were, so generally this is doing nothing but tracking. There's nothing, it doesn't affect the properties of this polymer. So I don't want to bore you, so there are many questions being answered since 2004. And many of the leading phenomenology was discovered only since then. So you can imagine, if you don't have the basic phenomenology, how can you build this field in terms of what it happens? So I'm not going to go through all the details at all about it. So at the end, I'm just trying to indicate two cases that, so how did we answer the question, or how much we answered? Not sufficiently, but at least it's a beginning. Basically, there are disentanglement that take place due to force imbalance, and it can occur in a localized manner. So quickly, that's what it is. I start to tell my student that that mother, rheology is mother of everything else. What I really mean was, by playing with rheology, we become sufficiently informed about the structure of polymers. It's made of a bunch of network, because of the uncrossability. Your noodle magnifying 1 million times is at that moment how complicated that system. But because of uncrossability, you have established a cohesion among our chains, one linked to another through this kind of uncrossability. And the relationship is time dependent. So we learn also it's all a matter of how fast you are deforming relative to how fast they can pass each other. Okay, so this gave us almost unique experience about how to think about this black box in terms of structure at the chain level. So I don't know, I keep saying God was watching us. You have to do it in this sequence. Finish learning what rheology is about, getting maximum information from what rheology teaches you, then you can move on to the next subject. Unless you do so, you won't be able to solve the next problem. The next problem is highly difficult. It basically tries to ask the question of, gee, how this solid all of a sudden is being forced to flow, Or is it able to flow, become the question. And so, of course, just for general information, your polymer, this is all plastic now, right? Uncross-linked, when you do processing, it's so that you can do processing. They are either glassy, amorphous, or semi-crystalline. They have their own set of issues. But generally, it's all about their mechanical characteristics, right? So a kind of a trivial thing to make a connection about is I just spoke about rheology. Rheology is a molten state. You have this random coil inserted into each other. They are moving actually, but they may move so slowly when you deform it, they look like frozen. That's why it look like a network, could be. We worked out the details, the pioneers worked out the details. They realized that you can characterize that without worrying about chemical structures. It turns out you can parameterize it. For example, you can use viscosity, you can use how entangled it is to suggest that no matter what polymer you have a network like I depicted in the melt state. They're all going to look similar, and therefore can be treated in the same way. So physicists loves it because then there's universal treatment about it. Deeply appreciating your polymer is made of such objects, you now cool the very same material to TG, to below TG. Take the simplest case, no crystallization. Wow, you would immediately agree with me that this is still there. Of course, it's still there. Nothing except now, maybe better for you to treat. Now it's not even able to move now. Okay. The additional physics is the fact they are trapped. They're not able to move because they are in the glassy state. And you can have your different polymers having different glass transitions. So it's chemical specific. But as long as you are in glassy state, you can also ask the question, can I parameterize it? So that I have a framework to address all polymer in glassy state, in the amorphous state. So once again, I remind you, in rheology is very successful. You just, everything depends on how long the chain is, turns out, how flexible they are. And then the rest of temperature dependent is just a matter of parameterizing in terms of friction coefficient. So you can build a theory that applies to all polymers. It turns out, and the degree of entanglement is just a matter of how long it is. It turns out, elegantly, all your polymers in glassy state can also be parameterized in terms of structure. Moreover, the structure actually is universal. All glassy polymers have the same structure. By that I mean, I will probably explain later more about the fact that, for example, what I mean by that is that the spacing between junctions is proportional to cone length, or proportional to chain flexibility. As a result, this ratio, this I have to sort of explain much later, but at this point, what you need to know is anytime you have a piece of sample, you can imagine a plane cutting through it. Then, of course, all the bonds are sticking out across the plane. That's all the solid red. That's all the bonds. Some are at a different angle, but they all occupy, so that your space now is covered by all the bonds. But not all the bonds are load-bearing. Only the network are load-bearing. Therefore, the actual load-bearing bond is only a tiny fraction of the bond that's occupying the plane. And that ratio turns out can be worked out to be related to the cone length over this strand length. And that, as I said, that strand length turns out to be universally proportional to cone length. Therefore, this ratio is a constant. So all polymers the same, can be treated the same. This is exciting to demonstrate, to show. So let me give you, the rest are, you know, what progress did we make, right? So this is one of the book, relatively early. it discusses it. It recognizes the following, that if I think about a piece of material, what is my wishful maximum ideal strength? It turns out you can calculate, you assume all the bonds bear load. Each bond bear load to the point until the chain breaks. You get 17 gigapascals through this formula. Okay? And it's stated in the book. However, it's known since 72, this figure, famous Vincent plot, it's known since 72 that your dear polymer do not show 17 gigapascals, it only shows 150 megapascals of stress, of strength at which it breaks, 2 order magnitude apart. This is confusing, to say the least. In fact, the confusion comes from the first mistake. We should never compute our ideal strength as 17 because not all the bonds bear load. They know that. They also know, perhaps, or they don't, rather, in fact, not the breaking that I just showed you for the polystyrene, it doesn't mean the bonds are breaking. So that is something that they didn't quite know. They don't know that this doesn't necessarily involve bond breaking. So in any case, at the end of the day, there were 2 pieces of confusions about worrying about, gee, just how come only a small fraction of the bond break, or what? And they keep saying, oh, there's just only 1% of the bond break. And this discussion does not have any picture of the fact your polymer is a network. A chain, look how I carefully draw. A chain, for example, the red chain, it folds back and forth on the plane many times without bearing the load. You can only count it as bearing load once. Okay, so this is a major piece of information missing. You have to have a network concept to properly count the way the stress arises. Okay. So in any event, this is the second book doing the same thing. They said, Jesus, there's a factor of 100. 1% of the bond are breaking. What's going on? Any of this puzzle that they make shows the lack of the picture of a network. That there are load-bearing bonds and there are non-load-bearing bonds, and you need to properly understand that. More disappointingly, if you carry on further, remember I just said the ideal strength is 100 times larger than what I observed. A convenient thing to do is to blame that there is a fracture mechanical origin of this, that you have flaws. And this is why you can see necessarily, even talking this topic, I will have to talk about fracture mechanics eventually. Of course, that's also turns out to be what's most exciting that we're working on. So in any case, this is, again, every book is discussing this without realizing what we learned from polymer rheology, that this thing is, through uncrossability, form a network. So let me go to the second difficult topic. The first topic was about structure and strength, and there's plenty of confusion there, as I showed you. Secondly, this most strange thing, this I have polystyrene here. If you take PMMA, it's also brittle at room temperature. But if you warm up to 50, 60 degrees, it turns ductile. Simply turns ductile. All polymers have this point. Different polymers have different temperatures at which this happens. So I call it BDT, or so-called brittle ductile transition. This is a textbook, only 10 years old, saying, oh, somehow the ability to undergo plastic flow is happening at the same time with process that will cause it to break. These two compete. The ones that require lower stress wins. Highly unsatisfactory explanation for why at a higher temperature is ductile, at a lower temperature is brittle. And I guess I feel probably, so I don't know how I should feel. But in any case, the more amazing thing is this textbook praised this explanation by saying, hey, look how wonderful this argument is. It allows me not to talk about fracture mechanics anymore. It bypasses the relevance of fracture mechanics. And that statement merely, you will soon judge by yourself, means he doesn't understand the nature or the essence of fracture mechanics. And this has become very, very alarming because we even later had reviewers at NSF making similar comments to kill our proposal, in fact. So, huge confusion. And if you want to go on, there were people speculating that this brittle ductile transition has to do with different polymers behaving differently. So that's just something additional. I'm not going to go into detail. So it turns out that there are 5 factors to affect this brittle ductile transition. I was just thinking that you may be enjoying this one. This is polystyrene. It's brittle, but once you pass through the two-row mill, going through so-called mechanical rejuvenation, like a magician on the other side, it's ductile. So that's common knowledge. It shows there are many variables in the problem. And I'm going to cut it short and just forcefully tell you that our appreciation of having a network in the system is essential. This network, this unit repeating 1 million times is my sample. And as I stretch, this network is able to become displaced and start to mobilize other segments so that eventually all the segments can wake up meaning they are no longer stuck. And then they can participate in flow. So that's the concept of flow, requiring a network. When it's too cold, you are not able to do that. When it's too cold, it turns out you build so much tension, the chain start to pull out before you succeeded in activating everywhere. So that's our scenario about brittle ductile transition. At least it gave us a logically tight argument about how it happens. The byproduct is what's most amazingly useful. The byproduct was this. If you think this is a network, as I just showed you now, you see the red chain, it goes back forth many times, but it's only counted as one bearing load. So your network, you can compute for what is the area density of your network. If you time the area density of network with the force required to pull out for the network to break, you get a stress. Stress is force per unit area, and that thing is force per unit area. It's the force of each strand that bear load and how many strands per unit area is there. So you put the two things together, you can compute for what this stress should be. And it turns out that the language to use is, for example, I did it okay, each of the bond occupy an area that's known for any given polymer. So the density of all the bonds, that's phi, is known for different polymers. What is not known is this network density. So I just give you a depiction. If this thing backfold 8 times, then the density of the network is 1/8 of the bond density. So we're starting to make progress. If that's the case, you have a theory. Wow, this theory fits the data. So in the old days, there was a piece of data I showed you, the Vincent data. It was plotted against phi, but they are proportional because Q is a constant. I just argued a few slides ago. For all polymers, this Q star is the same number. So this enabled you to say that this thing actually grows linearly with area density, meaning the pull force is the same.
If you have all these densities at hand, can you get a handle on the amount of free volume?
So it's this question of how useful that concept is. Perhaps I can say at the point of breaking, they all have the same free volume, and therefore, meaning, if you're thinking about free volume in terms of what determines what, also depending. So let me just dodge the question by saying that we don't know a priori that this theoretical formulation would work. That it turns out, for example, you see polyethylene or PET, you have to go to minus 100 before it becomes brittle. Above it, it's all ductile. And for polystyrene, you have to go to at 70. When it turns. So there is a question of why you got this pulling force being the same. So that's not something we have a theory for. So in any case, I just want you to visualize that we start to suggest. This should look familiar to you now. We start to suggest that I have a theory for what your strength should be. But we don't know the numerical numbers because this 8 is what I made up. It could be 10, it could be 20, it could be 30, we don't know. But it starts to give you a sense, maybe we're on the right track to think about the strength. And one of the leading things I want to intrigue you with, known for 70 years by now, is polystyrene is brittle, but if you process it, for example, melt stretch it in the same direction, and then you try to stretch in the same direction, it turns ductile now. And the theory that I put forward to rationalize this feature. So again, I'm going to run out of time, I guess. So I will wrap up this part. We have a sense what happens. The network is what can bring ductility, can make polymer flow. The network only exists if your molecular weight is high enough so that there is enough of this mingle, of intertwining of this uncrossability taking place. Minimizing, you can imagine now the chain ends. The end of the chain is a dangling chain that's not bare load. You don't want a lot of that because that one is a dead weight you need to carry. So high molecular weight is necessary as a result. Disappointingly, I want to report to you, we don't know why styrene is brittle, polycarbonate is ductile. That has to do with the nature of the glassy state, which nobody knows, as you know. The nature of glass transition has not been solved. It does not mean we cannot make progress. In other words, it does not mean, for example, I may just quickly actually get to the end of it. It does not mean industry doesn't know what to do. They biaxially stretch your polystyrene. It's on the market all over the place. Biaxially stretched polystyrene is a very flexible ductile film. It's no longer brittle. It has everything to do with bringing the network denser so that the job to activate becomes much easier. So it works, it works like a glove in hand. It really works in that way. So I'm throwing one of the questions here already. The way we formulated the theory is formulated as if what we calculate is the inherent strength. Because in my model, there was no defects, there was no nothing. It's just what the strength of the polymer should be. How does that compare with the experimental value? Well, we compared it, we see a favorable argument, but then we deduced that we have to play with the prefactor we don't know. This is all a scaling argument, so the prefactor is unknown. So this question is unknown, but it will lead us to tremendous progress later when I come back to the topic of strength. So that's the summary of this part. The strength depend on the network, the amount of chain tension that could cause chain pull out. And I showed you geometric condensation. It's a word I invented, very appropriately explains why polystyrene turns ductile. And basically you can drive a system ductile because the network can cause activation to take place. If they cease to do so, that's when you have brittle failure, which necessarily occur because the job to activate becomes more difficult at lower temperatures. So that's the logic. So did we answer this question? What caused polymer? Well, hand waving level, it is satisfactory for us for the moment. It is due to the fact that this network is doing it. And this is the one simple reason all your polymer must be of high molecular weight to have a robust network. So let me switch for a moment to the subject of semi-crystalline polymer. That's another place where we can exploit this structural property relationship. It's known for a very, very long time. Your polyethylene, well, the familiar one is your shopping bag. It's of course extremely ductile. It's drawable, and you can snag and all that. But if you cause the crystallization to go sufficiently high, this is Mendelkern's data, it turns brittle. So he was just showing when the crystallinity of your polymer of polyethylene is very high, very low, not low, for example 60, you can draw so much, and then it crashes down, no longer drawable, as it crystallizes too much. It's a major hint what's going on. It's almost a sufficient hint. The crystallization is destroying the network that's underlining. The network is always what connects at the global scale to provide cohesion. Through uncrossability, by the way, because there is no cross-linking. So I was pleased to just finish this piece of work because I'm not an expert on crystallization. Toshi, no, this is too complicated a problem. But I hang on to the question of preserving the network being the essential message. If you can preserve it, your semi-crystalline polymer will also be ductile and drawable. I can quickly say a word. One way to preserve it is to make sure your crystallization is fast enough. When the crystallization are slow or you crystallize too much, the system have a way to squeeze all this crossability away, make them disappear, right? Because if you just squeeze them and they have time to rearrange, that's what happens. So my mental picture was very clear. I still wish the simulation can do it. I'm still think in communication, perhaps even with Craig or whoever can do it. Imagine you have a semi-crystalline polymer. You can achieve this crystalline state in a variety of paths, in a variety of ways. I imagine all of a sudden, thought experiment, right? Simulation can do it. All of a sudden you melt it. You can ask the question, is the network as much preserved as the original network that you can perceive by taking a snapshot in the melt state? And the short answer is, by the time you have so much crystallization, you must have very few of this anymore. I still don't have the proof, but we work with that premise. It's going to work. That premise should work. And so basically you can trace it back. You can imagine you have a network, but imagine all this network means this part is crystalline, that part is not, and then you compare that with the original one. At least that's the guideline, and we use that to examine, once again, how you can preserve entanglement in order to achieve drawability, right? So that's the key part of it. So it all is about structure property relation. In fact, by now, the secret is already out. The structure, you want a lot of entanglement. You want a lot of network. good network giving you a good mechanical property. So now you can concentrate on preserving that structure or achieving that structure through processing. And processing has so many parts, right? It has temperature, has to do with what kind of polymer is increasing fast or slow, thermal history, morphology, everything comes in. At the end of the day, you want to achieve drawability. And the sample is drawable. You see, you have a lot of crystals. The sample is drawable only if you can get rid of those crystals by mechanically melting them away. And that can only be done through having a network. The more robust your network, you see, so it's a very, to me, it's a very fascinating topic, but just like anything else for polymers, we don't have molecular tools, so there's a limit how much I wish to do, since I'm not a big expert on crystallization. Basically, the crystal has to transform. And through the tight chains, whatever language you want to use, basically through the network, forcing it to melt down. Because what happens is, what I can you easily visualize, what happens is as you lengthen it, the cross-section has to contract. Okay, that's the basic story of shape change. As you lengthen it, your cross-section has to proportionally shrink. If there's plenty of crystals in there, they cannot do that. So you have to have the crystal destroyed. So we had one very nice success on this, right? This is truly remarkable in a sense you will hear soon. That is, I don't know why it keep changing the aspect ratio one. This is a video problem. So in any case, we know so well about rheology, so we realize we can make chain to elongate, to orient. Once the chains are oriented, it induces crystallization. So we end up designing a system that crystallizes on nanoscales at the level of the mesh size of the network. So the crystals are necessarily nanoscopic. You achieved many things. Geometric condensation is achieved through the stretching. So this poor, very brittle PLA become a very tough, transparent, heat-resistant cup. TG is only 60 degrees, but we have crystallization on nanoscale. Crystallization means the TM to melt the crystal need 150 degrees C. So no problem handling boiling water. So we're still in the middle of perhaps getting to the point where we make transparent plastic cups that can hold hot coffee. Such a thing does not exist in this world, actually, at this point. And it's sustainable because it's PLA. So the last point that I was saying was this theory that I built and demonstrated to work actually explains what it was invented in the 50s by DuPont, so-called Mylar. They did the so-called biaxial stretching of PET. And it's highly heat resistant because it has nanocrystals. It forms in the same physics that I demonstrated here with PLA. It's a very successful product. Everyone knows about it. It's called Mylar. Heat resistant, transparent, and strong. So, yeah. So it's a matter of, this topic is really a matter of avoiding destruction of chain network, right? To do that, to preserve that, you better have fast crystallization. This is why polyethylene is so wonderful. Even PP is semi-wonderful. It's relatively fast. But if you can slow down all that, disaster can take place. And if you have too much crystallization, disaster can take place, such as what you see in PHA type of materials. But you see some examples of exactly how we're trying to carry out this chain of processing structural property chain. So we don't have quantitative answer, but we have some feelings about the fact that crystallization depletes entanglement. And of course, Toshi knows entanglement conversely also hinders crystallization. So there are a lot of to play because if you have a lamellar, at least in the lamellar, you cannot have you cannot really tolerate chain crossing. So they are all squeezed to the amorphous phase. But you could have too much squeezed away out, not out, disappearing during the crystallization, that there are not enough connectivity anymore, translating to not enough tight chains per unit area. Then you have a problem. So the last part, I indeed could spend, you are giving me another hour. The last part, the most fun part, indeed, in theory, could take half an hour, could take an hour, depending on how slow I do it. But this is our current things, so we are very passionate about it. And so I want you to hear the full story of it. In fact, I think in the glassy case, you have a sense of how we had a really satisfactory progress, if you will call it. And rheology was a thing that I didn't say too much about what is known prior to our observations and what is the theory and how much of this discovery of rheology was earth-shaking, meaning contradictory to established notions. I didn't say too much about it. This last part, I hope you could enjoy in its totality, all aspect of it. So I will try to slow down. I certainly have enough time to talk about it. And the subject is so young for us. I started to have, due to pandemic, started to have a quick look at what is going on in fracture at near the end of 2020. This is fracture mechanics of fracture is a very large subject. I usually shy away, so I dare not to touch it. It's not a burden from pandemic, but it's just an opportunity that I had the luck to almost like by accident start to look at this problem. Not so accidental. We thanks people who organized webinars during the pandemic to keep ourselves busy. And they organized this wonderful webinars on fracture type of things. And one of the speakers I know very well, so I attended it and start to feel maybe there's something to it. And then, thanks again to pandemic, it will not happen again, usually, because pandemic, a course at Harvard on fracture mechanics was offered on Team, or rather on Zoom. 1/3 into it, I was told by my friend who is the instructor, hey, I'm teaching it on Zoom. So I signed in as a little 22 years old student listening to that course. And I start to lose sleep upon listening to it. So, of course, we knew each other, so the student was enjoying us discussing at the end of the class. So we had fun as I pick up this topic. This part, I can collect tuition from you. I mean, really, in the next hour, you will learn literally all the essence of fracture mechanics, which I shied away for 30 years. The essence is all quite trivial and quite easy to remember what happens. So here's the essence, right? Fracture mechanics was discovered or established based because of our desire to explain one thing and one thing only. That the strength, your nominal strength, seems to be very low. Remember, I raised that question from in the beginning. The last question was why our polymers are not stronger and tougher. So generally, no matter you have a piece of plastics, your thermoset, or your elastomers, tire, vulcanized rubber, you generally find the strength, which is nothing but the stress at which it breaks, is not very high. Compared to what? To compare what you wish by theory. I say theory with a quotation mark, and you will see why that is the case. Generally not very high, our polymers. But it all started 100 years ago by looking not at our polymers. I mean, we hardly have any polymers. Stallinger hasn't told us there's polymers. 121 years, 1921. They worry about the fact the window glasses, silicate glasses, is only as weak as 100 megapascals, although the theory tells them they should be 100 times stronger. And that theory is reliable. For you see, window glasses, basically you have an atomic bond. You can, I even wrote that down in my second book in chapter 8 as an introduction. You can derive and show the strength should be about 1/10 of the Young's modulus. We know the glass Young's modulus is 70, therefore 1/10 of that, it should be 7 gigapascals, 2 order of magnitude larger. So what facing them beginning of last century was to explain this. And the take-home message for this part of fractional mechanics is if you have flaws, I will explain in detail, if you have flaws, then you could have this scenario that your nominal strength is not as strong, as high. So essence of fractional mechanics, one, that your strength you suspect is much lower than what you can get. Two, your material behave this way lower because you have flaws. So in 1913, this is the most celebrated paper. English considered trying to solve this problem mathematically we probably have enough notion that if you have a defect, meaning if you have a piece of paper and you're really trying to dig a hole through it, then that sample will start to be weaker. In the following sense, the stress at the tip of that hole, this is a through thickness hole, will be larger than the nominal stress by a factor given by this formula. And A is the size of the hole, and rho is the curvature of that hole. Okay? So this is a theoretical result. And if you just push this formula to the point of fracture, right? Just push it. The nominal load will reach a critical stress, and due to this hole, sample will break. One trivial way to say is it breaks because at the hole you reach the inherent strength, meaning the maximum strength you can have. And this will necessarily be larger than the applied load if A is much larger than rho, right? That's just a mathematical demonstration of it. This result, I don't know if it's intuitive to you or not, but this is a mathematical result for an elastic object. So this would potentially beautifully explain why window glasses are weaker than what we could achieve in absence of flaws. So through this whole thing, you can even imagine the flaws in window glasses is about 1 micron or so. This is I'm just trying to cover so that you can complete this thought process. The problem with this is, for the reasons that I have yet to communicate with all the experts on fractional mechanics, is they were very much bothered by the fact if the tip is become infinitely sharp, then the stress will be infinitely high at the tip. Or conversely, your material will break without me loading any amount of force. That's the same statement, meaning 0 times infinity is a finite number, right? So basically, they were very much bothered by this expression that if my cut is very sharp, my flaw is very sharp, this has become unphysical. So indeed, Griffiths, who is considered to be the father of fractional mechanics, didn't like English result. I will hopefully even be able to say today, English result was sufficient, but Griffiths didn't like it. So he uses English solution to come up with some other way to establish a understanding of what fracture mechanics is all about. Well, fracture mechanics is all about having a piece of sample innocently there, a pristine sample. But you imagine there are flaws in it. You imagine you have flaws, okay? And if there are flaws, English consider just like, Griffiths consider just like English does, why not I just intentionally make a flaw and see how flaw weakens the material? And the argument is very, very simple. If you play with the concept of so-called surface tension or soap bubble, anytime you increase, create a new free surface, you need energy. That's the surface tension. Okay, so that's the same as you blow a soap bubble. The reason you can blow it is you do the work. You're pumping more energy so that your soap bubble can be bigger, more free air, surface is created. So he visualized it that a crack at this tip will, in other words, instead of A, it will grow to A plus delta A if the additional surface created can just take advantage of the fact when you have a bigger crack, there will be energy released because the amount of energy you store has to do with all the unbroken part. If you break a little part, you will release some energy. All elastic energy. So the whole idea was, if I want to conceptualize, is you load, you stretch, it's an elastic material. So based on basic linear elasticity ideas, it turns out you do work, the work is all stored as elastic energy. And when the cut grows, you will be able to, you can only store less energy now, which means any growth means you will lose that much energy. And that energy can be used to pay for the surface that's appearing. So by that argument, he was able to recognize that what's important is this G parameter. And he wanted to compare this G parameter with the surface tension. So basically he says, oh, you can keep stretching it. As soon as you stretch it enough, you will store enough energy to pay for the free surface. And that's when the fracture occurs. So in the window glasses, it turns out this GC is nothing but surface tension. So just pay attention to the unit. It's a funny unit called energy release rate. It has the dimension of stress times a length. Okay, stress times a length turns out is the dimension of surface tension. So he found by playing with the window glasses, different cut size will give you the same GC, implying that larger the cut, the weaker it is. If you increase your cut size by a factor of 4, the fracture will occur at a factor of 2 smaller in stress. That's the celebrated Griffiths scaling law, the most well-known key result of fracture mechanics is this law. So equivalently, you can introduce a equivalent concept called K, which is just speak about the same idea that essentially accounts for the fact the prefactor for this scaling is that Kc. So now you have the Griffiths law for window glasses, and the success of Griffiths was he indeed found this GC is surface tension. Okay. So he go to his lab, he used different cut size, You find the larger the cut size is, the lower the stress. And you find this curve is exactly a curve where the GC is the surface tension. So this is a big success. No question, everything is working. Except when you have high strength steel and polymers, this GC is much larger than gamma. I lose sleep over this upon the teacher teaching me this part. Yeah, this is the crucial part. What?
Griffith's theory is really for a homogeneous system.
Quite the contrary. This whole thing, the problem they face is to explain why my nominal strength is much smaller than ideal strength.
No,
Yeah?
Griffith's theory is based on a homogeneous piece of material in which you have
It's not only homogeneous, it's linear elastic. Right. It's completely homogeneous except the crack.
homogeneous.
Except the crack.
Network glasses are not.
Huh?
The network glasses are not.
Window glasses,
Well, they're silk glass, but I'm talking about the polymeric glasses.
so now you are free to imagine anything you wish. So the point is, other material shows Griffith's law works, except the involved constant has nothing to do with surface tension. In other words, man, I can break, I give you all the energy you need to form a new surface. No, it doesn't break. 100 times it doesn't break. Sometimes it's 1,000 times larger is when it breaks. So if you read the literature or textbooks, this become a tremendous confusion. So what's going on? Why all of a sudden I need much more so-called energy release rate? I probably want to leave it as such, except to indicate to you that different polymers have different values. So you can have A, B, C, D, and Griffith's law works. What is not known is that constant Kc. Different material have different Kcs. Okay? And you cannot figure out what is that determine the different Kcs, because Kc is measured operationally, meaning Kc is just when your sample reaches some critical sigma c times the length of the crack. So you have no insight about what is, how to think about the magnitude of this Kc and why it varies from one to another. So I know you guys probably say, oh my God. Again, don't try to absorb all the information, just the one that interests you, and just pay attention to the main message, right? So in any case, it's only a few years ago we celebrated 100 years of fracture mechanics, generations of huge number of researchers working this field, because many different materials may all suffer the problem of fracture. So the polymer is just one type of material. So I list some names in general and some names regarding polymers. What I want to tell you is that our earlier researchers working on polymers all heard about Griffith's idea and all automatically agrees our polymer is weak because there are flaws, because that's the essence of picking up fracture mechanics. Implying very rapidly that I know my polymer should have been much stronger. You see my point? Meaning, whatever I observe and measure that nominal strength, I don't accept that as the strength I can have. Let me blame the flaws. So it's all over the place, over flaw size. And I bring this back, a comment I showed you earlier. remember I told you there was a two. Do you now recall? We showed there was a 2 order magnitude difference, remember? Except that 2 order magnitude difference, did you not see what my notation was? That 17 gigapascals? That's the limit of a polymer fiber. When all the bonds are lined up to low bearing, to have low bearing. Your dear polymers that I just broke for you, this polystyrene, is a coil in its isotropic shape. It falls back and forth many times, wasting all the areas you have. Do you start to get it why your polymer is weak? It does not, it occupies your area per bond, but not loading it properly. It's loading at the van der Waals level. Except for the few that does bear load. So, in any case. So that 2 order magnitude, as I said, is totally misleading because that was an irrelevant limit of polymer fiber. You should only compute for a theoretical limit of your strength in the isotropic state. And then ask whether they are still 2 order magnitude apart or not. But since we just heard they are 2 order magnitude, here this one says one savior of that is blame fraction mechanics, meaning blame that you have flaws. Now you see the circle of the logic here now? Let's invite flaws into our problem, then we are solved. All the problems are solved. So I even today carefully read the first paper on fraction mechanics of our polymers, first in plastics. There will be another first for elastomers I mentioned later. So this one basically exactly see, did you see 2 order magnitude? That's exactly the 2 order magnitude I was reviewing for you. And one way out is to follow fraction mechanics. Blame flaws. And he indeed do that. He cut his sample and find this curve that I schematically showed you. The strength, sigma c, versus the size is square root of it. Okay? By the way, if you look at the Kc, it's much larger than surface tension. The logic of doing fraction mechanics is that you use a pre-cut sample to measure Kc, and you can use that same Kc to predict an uncut or unnotched sample by assuming there is a flaw using the same formula. And you conclude that your dear polystyrene sample, which is this one, would have flaws of 1 millimeter. Do I see 1 millimeter here? That's gigantic. So you run into some illogical, you run into some logical circles here. The logical circle being, for this theory or this account to even hold, you have to independently theorize what flaws you have there, right? By visual inspection, when you don't see anything. Okay. So this is the Vincent plot I showed you before, and I'm just reviewing for you, looking at the PMMA. Look at here, PMMA data is this one. It has a nominal strength about 60 megapascals, okay? 60 megapascals. Is it too low? Foundational question now, right? Is it too low? You cannot answer this unless you do know what is the theoretical strength, right? Therefore, are there flaws? So you heard about brittle ductile transition. I want to bring you back the SF reviewers' criticism that killed my proposal 10 years ago. It says about me explaining brittle ductile being the network driving activation to take place. The reviewer says, go back and learn fracture mechanics. Today, the short answer, it takes some time to digest. Fracture mechanics, you already know the essence of fracture mechanics. It's about flaws weakening your apparent strength. It has nothing to say about how a sample can turn from brittle to ductile. That's a polymer physics problem. So a bit of a madness there. So the interesting part that I want to draw a connection is this study of brittle ductile transition, at the end of the day, provided the new insight about how to think about fracture of polymers. Because I remember I said, as a byproduct of that model, I, by accident, calculated the inherent strength. So the rest is something very remarkable, I tell you. And therefore, I can indeed try to answer the question, is 60 megapascal all you got, meaning the theoretical strength, or much lower? So therefore, is a material being brittle has nothing to do with fracture mechanics, folks. I mean, so in any event, this is the textbook. It has all the prevailing understandings, and the question is that understanding obsolete or reliable or not? So the two questions focusing on this is, once again, do we know we have a strength that's too low because you have flaws? And yeah, scaling law works, but do we know why this toughness is much greater than surface tension? So that's just two questions. Here comes the fun part, right? This is almost like doing a repeat of the slides. In the fiber limit, you can do a simple exercise because you know your bond area density, you know breaking a bond is several nanonewtons, you know that fiber to break it will require 15 gigapascals. And we only have 100 megapascals, so 2 order magnitude apart, except this is a fiber limit, as I said. It's not a calculation of the coil limit. So here's the fun part, right? So therefore, the question is, how do we understand your nominal strength is so much weaker than fiber limit? Well, that's a pretty dumb question. The fiber is a fiber. It's not an isotropic state. And indeed, people can achieve fiber close to, easily, 5 gigapascals. So it's only a factor of 3 apart from theoretical limit. So this is clearly human ingenuity, polymer fiber. That's no question. They utilize the bond strength. They all lined up like chopsticks. So here comes the fun part. Do my model that I just showed you, it should be add network density times the force to pull out the chain, not breaking it. Because when the tension is enough, they have the freedom of simply disengage. They don't have to break. If the force is much smaller than breaking, then of course they will not break. So I claim, this is known for 10 years almost, I claim that, see how I write it. I write my theoretical strength as related to the fiber strength by these two factors. One is that area density ratio that I once showed you, because the chains fall back and forth. They are not in the fiber limit. They don't bear load. They waste all area. What a shame, but that's what coil means. What if that ratio is 10, a factor? In other words, it falls back 8 times, 10 times. Second, what is that pulling out force is only 1/10 of the force to break it. Okay, just allow me to speculate. 0.1 times 0.1 is 100. If so, I claim what I calculated as 60 megapascals is all you get. Fiber limit is an irrelevant apple. We have oranges. So let me remind you these two questions, right? Whether it's flaws or not, whether the strength is too low or not. And then we want to answer the question why GC is much larger than gamma. Well, it turns out the way to answer the second question is already emergent from the first question. And I will show you that part. In other words, if the nominal strengths and theoretical strengths are similar, in other words, you cannot blame flaws, it turns out that resolved the second question. So I will show you that. So the whole game boils down to figuring out what is the theoretical strength so that you can compare with your nominal strength, so that we know fraction mechanics is in the game or not. Yeah? I just told you, Puru will know too well, it's a scaling theory. I cannot theoretically be sure that I have a factor of 100th times the fiber strength. I cannot be sure. I have everything matching, but this is because I played with this arbitrary scaling factor to match it, and claim my chain pull-out force is 1/10 of the breaking force. So the question 3 years ago becomes whether we can try to do that by experiment. In particular, if you have this notch or crack already, can I dream of determining the stress at the tip, at the point of fracture? The rest, you believe me or I believe you, the rest you have to accept my suggestion that upon breaking, the stress, if I can observe it, at the tip, should be the theoretical strength. Fair? I can repeat a million times in the sense I will get lucky, make sure that at the tip there are no funny things going on. It's the inherent, it's the homogeneous. By that point become very important. So this is the premise that I'm going to try to measure the stress at the tip. This has a very large background. If you propose that, if you're expert in fraction mechanics, as people have been doing, they will say, go home, don't even try. You won't succeed. The general knowledge is the stress, you can never determine the stress at the tip because the stress at the tip will keep increasing beyond you can resolve it. So that's the general impression of it. But nevertheless, we had that desire and we start to look at it, and we know using birefringence is a way to report the deformation of the structure. And it turns out that deformation of structure through give you birefringence, and that birefringence can linearly correlate with the stress. And what was surprising twofold was the stress does not keep building. So what's plotted is r minus 1/2. Therefore, to go to the tip is at the infinity to the right. That's r equals 0. But it's r to the minus 1/2. So to infinitely approach the tip is to infinitely go into the right. And the stress does grow up, but then stop growing up at some point. Aha, that's a aha moment. It means you can claim to have accessed the stress at the tip. And more importantly, find that stress at the tip grows linearly with the load. The more you stretch, the higher the tip stress, linearly. We all know how to write a linear equation. It just means that there is a prefactor. They are linear with each other. There is a prefactor. K has a unit different than stress. Therefore, this prefactor is not dimensionless. Here pops out a characteristic length scale. This prefactor is necessarily a dimensional quantity because the two quantity doesn't have the same unit. So Yale at U says there is a length scale coming into the problem, and that's P. And this length scale P. So here comes the question that we're trying to answer here about the strength, about the toughness, why it's much larger than surface tension. So you look at this expression, K is determined by how much you load and the cut size is there. And you drive this linear relationship works all the way to the point of fracture. So you can imagine now your K keep increasing, which means the sigma keep increasing. On the left side, the tip keep increasing until hitting the strength, right? When it breaks. Carry that equation all the way to the fracture point. On the left is the inherent strength we hope to measure by experiment. On the right, K reaches Kc. By definition, is when the load reaches critical load. So we achieve two pieces of information. First, you determine the tip stress at the fracture. You can compare that with an unmatched sample of the nominal strength. Cut the story short, we find that to be similar. 40, 50 megapascal level. More importantly, look at this powerful expression. It actually says how Kc is what determines the magnitude of Kc. Isn't that astonishing? Remember, we just said we don't know what determines Kc because it's just, if you just measure sigma c and a, that's operational. That's just the measurement. Now we know what determines the Kc is the inherent strength times the square root of this characteristic length. Some progress. So in summary, this is really should be a new textbook version. This is what we know for 100 years. Okay, the so-called toughness. Allow me to just define it this way. It's just notational change. It's the same thing. What it does say is toughness is operationally in the field of fracture mechanics given by the critical strength and the cut size. It's operational. The bigger the cut size, the smaller the sigma c. In combination, it gives you this, right? It nowhere it tells me why I should have this number. And the reason you have this GC is because stress is no longer sufficient to describe the problem because a length scale comes in, which is the cut size. So it turns out it requires a combination of a stress and the length, the pair, that define the toughness. But what we uncovered is there's another pair. The pair of the inherent strength and the tip bluntiness. In other words, when you have a crack, you don't introduce one length scale, you introduce two. One is the size, one is the curvature. So it turns out all that physics is already in the English solution. So in any case, I hope you have now a sense of a much greater insight about not only just how Griffith's law holds, but how this prefactor is determined by these two material parameters, and therefore structure. So lastly, I think we are all pretty tired by now. This part perhaps is more remarkable, but I probably will try to cut it short. Say a few about it. Now comes to the elastomer. I'm so proud to tell you, I mean, at Akron, we're supposed to be the world center for rubber study. I worked for 30 years on the faculty, only studied the rheology of rubber before curing. I never studied rheology or mechanics after curing. So this fracture mechanics finally bring us to what should be the core of Akron polymer, elastomer. The trivial question, again, is the same. This is the piece of 3M commercial elastomer. It's pretty strong, but I ruptured it. Is this rupture a fracture mechanical problem? By now you should know how to answer it. How to answer it? Remember how to answer it? I'm asking, is this a fracture mechanical problem? Remember how to answer it? It's all about my hands felt enough force. It's all about what's the strength of this relative to what? Relative to what you ideally thought it could be. Yeah? And as my opening statement, is your elastomer strong enough? Or damn, it's actually not strong enough. How come? So it turns out it's the same exercise, this time realistically. Only in the coil limit, not fiber limit, you can estimate the strength of your Gaussian chain network, the classical phantom chain network. I'm not going to go through the arithmetics. You will find that innocent, not fiber, innocent Gaussian coil form elastomeric network should have a strength of 3 gigapascals. Trivial to demonstrate, okay? I'm not going to show it here. I showed it here, but I'm not going to insist you follow through it. Should be 3 gigapascals. What do you normally see? A factor of 100 smaller. Man, don't you want to invite fracture mechanics back? Here, no cheating now. You should get 100 times larger. And you don't. Nobody does. What's the problem? So as if only 1% of the bond is bearing the load at any given moment. And today, perhaps everyone in the field would agree that is the case. Meaning, you're not going to get 3 gigapascal because the network is very heterogeneous. There are a lot of small strands that first get a lot of tension and break, and then just break one at a time. This analysis of 3 gigapascal is completely false because it assumes all the strands bear the same amount of load as high as breaking the chain level of load, which is, of course, idealized and turns out to be highly and entirely unrealistic. So if you ask today, people will say, I agree with you. It's not a fracture mechanical problem. It's 1% chain keep breaking and domino effect, and eventually fracture happens. So I know I'm running out of time. It's exhausting for you. So let me just summarize the astonishing phenomenology that we know about elastomeric. For 70 years already. 70, okay? It is known that this sample, if I stretch it very slowly, it breaks early. If I stretch a lot, much faster, it will break at a much higher amount of stretching. It's known for 70 years. And similarly, if you make a cut, you find the so-called toughness, GC, is also much higher if I stretch it much faster. First, that's first. Second, the very same sample, if you go to a lower temperature, you find you can stretch much more. It's much stronger and much tougher. These two facts known for 70 years. The dominant explanation is homegrown. I wish today Frank Kelly is here. His PhD advisor was responsible for this entire situation. That he was playing with a piece of a sample near glassy state in creep mode. In other words, creep mode means you use certain force. Of course, if you go to lower temperature, it will take a longer time to creep to the point. And this has led to a theory that says if your chain relaxation is slower, it's more difficult for the chain to it's more difficult for chains to start to build up tension. And therefore, you delay fracture. And that notion is a theory exactly 60 years old. The rest is incomprehensible for me to explain to you. The rest is somehow commensurate with this idea. People thought this two effect indeed has everything to do with polymer relaxation. And lots of people worked on it. You can read the two books. The fracture process is dominated by viscoelastic effects. Internal viscosity is higher at higher temperature. It somehow impedes the arrangement of chains, and the chains somehow could avoid being loaded. And therefore, you could explain these temperature and rate effects. So throughout the last 70 years, we barely ever talk about chain scission. Even though they seem to be even aware, eventually the chain is loaded to a level that it has to break. But they were convinced that this whole process has to do with building the tension in the chain rather than the chain breaking itself. Okay. So it's lots of work being done, including our dear Dejin worked on it. And so I think I will just probably flash this result for you. This is the first paper on polymers, the elastomeric state of polymers, dated even earlier, 1953, about 71 years ago. So they had a clever idea about how to compute for this toughness, because now chain is a very stretchable material, and the formulations people develop of window glasses would not apply, but they borrow this notion and find an ingenious way to take a measure operationally of this toughness called GC. And what they found as early as 55 is that this GC, lo and behold, if you stretch faster, the GC is higher. And if you stretch at lower temperature, the GC is higher. Okay? And I think my student can now appreciate. So they write it this way. They write GC as a function of the rate. You know, I'm a little bit picky and rigorous about doing science, about causality. About when you write y is a function of x, you typically imply x is causing y. You follow me, right? Cause and effect. Yes? You write G, the toughness, is a function of how fast you stretch, as if how fast you stretch is the input, G is the result, right? The consequence. I once even teased with a guy in fractional mechanics. He couldn't get it. I invite him to think F equals ma. Have you thought about what is the causality, right causality way of writing F equals ma? My acceleration really caused a force to occur? In classical physics. So this, come on, don't be casual. There's no room for casualness here. So cut the story short. I told you that we were, our grandfather, right? This is Frank Dilley's PhD advisor. By the way, at his time, he is a glorious figure, a dominant, towering figure in the field. And then, according to Frank, he quit all sudden at some point. People have the habit of treating this temperature effect by saying, look, why don't I just do a horizontal shift and construct the master curve? And by the way, that shift looked like a WF. I won't go into the details of this absolutely remarkable confusion here. I actually don't think I have all your attention to go to the details. But in short, I'm just saying that it turns out the problem is about loading your chain until the chain cannot survive. So it turns out that your bond has a lifetime higher than the age of the known universe. But if you stretch it, if you just straighten it, it's only 4 piconewton. The lifetime of that bond is still infinite. But if you load more and more, it will come down. According to density function theory, it will come down to your level. Look, this is how many orders? 60 order of magnitude, okay? And the force is normalized with maximum being 1, which is about 6.9 nanonewton for carbon-carbon bond. And the range you should pay attention is this relevant experimental timescale. So if you load this much tension, things will go. And so this much of the result is known since the 40s by the great Irving that proposed the concept of activation. So in any event, I think I will cut the rest of the story short in the sense you have a, for jam's sake, a rubber, you stretch slowly, it stretch this much. If you stretch fast, it can stretch more, okay? You go to lower temperature, it can stretch more. These two facts. Clearly indicating that the external timescale is relevant. The question is, what is the internal timescale? So previously, thanks to Beeke's theory and the blind fit of WF, people thought the internal timescale is the polymer relaxation time. Never realizing that another timescale is simply the bond dissociation kinetics that controls the lifetime of the bond and the network lifetime. So it turns out, I'm not going to get into all the nitty-gritties. So basically, you can find that it's a self-feeding thing. As you stretch more, the lifetime goes down, and eventually the lifetime matches the time scale that you're doing the experiment. At that point, this thing will give up. And if you do it faster, then stretching to the same level, the bond hasn't, you spend much less time to reach that bond tension. The bond says, oh, for this tension, I can last much longer. So you keep stretching. And so the temperature, because it's in here, the temperature is the thermal agitation. It greatly regulates the bond lifetime. Okay, so you can go through the whole thing. Basically, you find that this is the theoretical results, and it all agrees with what the experiment shows. Okay, so I would just want to finish off there, and some of this key aspect of this way of looking at fracture mechanics is already published. So in short, the polymer does show pretty disappointing strength, but that strength is all you get. You cannot blame the flaws for it. When you make a big cut, have a big cut, you will find fracture mechanics does explains why a big cut can lower the barrier. And I know this has been a very long time now. So in short, basically, let's complain about polymers not being strong, and we somehow have to improve the structure. In the case of elastomers, you have to get rid of this heterogeneity. In the plastic case, we know how to strengthen the polymer. So let me summarize. So basically, your polymer is not strong largely because you have a poor state of being a coil, where strength of a polymer of any material is force per unit area. If that area is all wasted by your chain coming back and forth without load bearing, how can you have strength? And this is the ingenuity, this is the amazing application of fiber, polymer fiber. They try to make sure that you don't waste any cross-sectional area. So you do have very strong material by the time you have a fiber, but not when you have an isotropic state. Okay, and so for elastomer, it's also disappointing. It's weak because it's not homogeneous. So the fact they are not tougher is tied to the fact they are not stronger. I derived for you for the first time that the way to appreciate the toughness, operational definition will never give you the insight of what toughness is. It's given by the other pair of the parameters, the strength of the material and the bluntness of the crack. Both are material specific. Yeah, so with that, I think I can summarize. Basically, we learn from rheology how to think about structure of polymers, and rheology indeed tells us that structure, even though it's a liquid state, can break up in a solid manner. You see, it breaks up discontinuously when you try to extrude the material through here. And you can indeed improve that ductility or make it more flowable by either changing the relationship between the monomers through modifying the glassy state, or structurally by pre-stretching, for example. And finally, this fracture problem really causes us to further relate behavior to structure and think about how you can improve the inherent strength and not worry about the flaws, so to speak. Okay, so I think that's all. The next one was just a teasing cartoon. That's all I think I have. Yeah.
Thank you so much.
Thank you.
Any questions?
Yes.
I did have a question, which was going back to one fracture case where it was, you have this relationship between the length of the fracture and it's all concentrated at the tip of the fracture point. But the way that we're talking about the fractures that would be inside of our homogeneous medium are as if there's thousands or millions or some large order of these fractures centered throughout the medium, and that Griffith's law, I don't know what the relationship would be. So they would be relationships with each other. So I was wondering if that ever added in or factored into
Okay.
thinking about this. But it seems really it's all one big fracture. Actually, all of these hundreds of fractures inside the material.
Okay, so one of the, I hope I could answer you in a way to cover this point. I told you for window glasses, it happens to, what you find exactly agrees with surface tension. And therefore, so remember, I lost sleep over this. Two things. Why there is such thing as a constant GC? Why it doesn't change? Well, if it equals surface tension, of course it doesn't change because surface tension is a fixed quantity. Yeah? Do you follow this logic? In other words, I can use all different sizes, right? A larger size, I have a smaller reduced strength due to this cut. If I have a smaller cut, then my strength is higher. But the product of it is Kc. It's always the same constant.
But what I'm saying is that that works for one cut, but
it works for all cut sizes.
All cut sizes. But I mean, in the principle of the theory is to say that your polymers or your whatever homogeneous medium has many cuts within it, not just one cut, but many cuts that.
I think there's a bit of a confusion in what you're saying. You're saying in presence of the intentional make, there are still flaws? Then you do this. You make sure, operationally, you make sure the intentional notch you make is far, far, far larger than any flaws possible.
Well, I guess that's what I'm saying. Is that
that's the logic. You get it?
If you want to back up your theory about all of these flaws being internal, the additive process of those flaws giving you the result is now being dominated by a big cut. I mean, if you don't see what I'm saying, which is that there's the relationship between all these tiny flaws is different to the one big cut.
Well, it is assumed to be the same. That's the point, right? So, but let me follow. The logic is very tight. You take a piece of material, you find your sample is weak, and you suspect there are flaws. And they says, gee, why don't I directly study what the effect of flaw could be? So I go to the lab, I make a flaw myself. And that flaw is so large, all the intrinsic flaws are irrelevant because the ones you introduce will produce a much larger stress concentration, will cause it to break materially. So that's the story.
I guess what I'm saying is that I don't know the theory well enough to say what is the quality of two big cuts or many cuts versus.
The cut size determines how much force stress you need. Okay, so by the time the large cut induce fracture, the small cut, of course, will not. In other words, you can make many different cuts here. You find the crack will happen at the largest cut. So that's not the point. The point is now you find that that this combination always gives you a constant, right? Why it's a constant? Well, it's because it's the surface tension, so it's constant. But then when it's much larger than surface tension, the next case, right, your polymer case, we go crazy. And the answer is the following. This story so far, surface tension, that's involving one monolayer. So it turns out this fracture problem never involves one monolayer. It involves thousands of layers to the point that we are lost because a molecular theory, of course, cannot describe how it accumulates to 1,000 layers. Each layer is suffering failure. But nevertheless, that's the real physics here.
I had a question around something you said near the end of elastomers not being tough because of heterogeneity.
Elastomers are not being strong because there are many short strands that are first loaded and break, and the rest are not load-bearing at all. So any given time, it appears, we probably universally agree, only a few % are bearing the load and break. Yeah. And so this is where we beg the chemists to make samples that are that's going to avoid this.
Yeah. Are there any strategies that you're aware of selectively breaking those shortest chains in the network and without breaking the material?
If the short ones are broken,
or how to reinforce those shorter chains?
Exactly. I don't think we know how to solve that problem basically right now. I'm talking about, for example, just a pre-made polymer. You just randomly cross-link it. It necessarily have a very homogeneous structure. Yeah. We don't have all the answers. We just have some sense of what's going on here, as you can see. The problem, I always impress my students. There are 10 to the 18 chains there, 10 to the 18 chains, any given size of sample. Even the physicists don't know how to simplify it, handle it, reducing to a single chain problem. But it's not a single chain problem, that's the thing. All we know since Dergin is a single chain problem. Yeah.
So now I have a question. So if we just load the sample to a certain level of L over L0, just extend the sample to a certain level of L over L0, and just try to do a delayed rupture,
Yeah.
waiting for a long time to make sure that we reach to the bond breaking.
Lifetime.
Yeah, the lifetime. So now we are getting rid of the short chain. Yes. So if I unload.
No, that's the question. I'm not sure we are getting. No, why you say we are getting rid of short chains?
So
you mean they break without?
We reach to the bond. The main reason that the sample can break is that that short chains now are just are not in the pictures anymore because they are.
Sorry.
Breaking, yes.
Yeah, they're breaking.
Yes, exactly. So if I unload the sample, I mean, take it out and just do like.
Hold on. That's much of the unknowns. Once the short chains start to break, you will not be able to preserve your sample. It will just continue and finish it. So Asel was suggesting that this is a remarkable phenomenon, right? We learned when we do rheology, people told us we couldn't believe it and never understood it. A cross-linked rubber, you can do the most amazing thing. You stretch it before it breaks and hold it. Over time, it will break, and depending on temperature, you break earlier or later. Depending on how much you stretch, you break long or later, earlier or later. And Asel was saying, before it microscopically rupture and break, could there be a lot of short chain that already broke? The short answer is, the naive answer is no. By the time short chains are breaking, this thing will continue. You would have reached the point of microscopic rupture.
So if we run a test and we know that approximately when this is going to happen and I started this before, can we just...
Still, the breaking chance must be negligible at that point. Because after all, it's just 1%. Yeah.
Would this be a percolation problem?
It is percolative. It is percolative in some sense, for sure. The path.
The small chains break, but they don't disrupt the network.
They will. The thing is, they will pass the load around.
Yeah.
So yeah, I think along that line, you probably want to think about a network made of A and B type of strands, and have one of them being mechanical have mechanophores, then you can indicate which one is giving rise to what. So things can, it all depends on chemists coming into the story in some sense. In fact, my good friend would already say anything to do with chain breaking, that's not polymer physics whatsoever. We hate it, meaning since the Jin style, come on, we never want to think breaking a chain is part of a polymer physics problem. I mean, I'm saying it in front of polymer physicist Peru here. And that's just so insanely wrong. Or rather, we should move on. And I urged, with you being here, I urged very early on that we teach our polymer still the so-called entropic force. Oh man, we should graduate long from there, right? I'm talking about this part. Oh God, sorry. I mean, all I actually try not to do to warn my student. All we do teaching is the Jin style scaling in the limit when the chain is still a coil. Little do you mind, by the time it's straightened, it only involves 4 piconewtons. That's still 3 order magnitude below the level chain breaks. At that point, there's no conformational change anymore. The physicists think that's such a boring problem then, right? That's my interpretation of how people reacted to that, right? But all the interesting physics is all in there. Nothing but there. This lifetime of bond is all the physics that's there.
Blaming physicists, not engineers.
Well, engineers, if engineers cared, I wouldn't be standing here talking.
Engineers are the ones who discovered all this thing.
They discovered Griffith's works, but they cannot answer what is that prefactor. They don't. I talked with establishment there. I mean, they acknowledge they find this works. I didn't tell you all the subtleties. So the subtlety you didn't realize is the framework of fraction mechanics is all based on Griffiths, which is an energy argument. And my approach is a stress argument. These are day and night in terms of giving you very different insight. For example, the elastomeric fracture problem. You trapped it in a loop if you use Griffith's energy argument. Never get out. So there are many very intriguing aspects that I omitted, but you get a flavor of it. It's, you know.
One thing we didn't talk about, which I think may be very important, is that when you put a sample under stress, it's dealing with thermodynamic system. So what is going to happen is that there are regions where the load is going to be very different. I mean, it's going to be distributed not evenly within the sample. And you would have a larger, you can just treat it ideally as like one single fracture or anything like that. That's where
you really reminded me of mentioning that Griffith's argument, the textbook teach you, is actually derived based on equilibrium thermodynamics. By saying free energy being minimized is the moment of fraction. Of course, this has nothing to do with with the equilibrium thermodynamics. No, but you know, fraction mechanics is 103 years old. A field much older is called mechanics, meaning not worry about the inherent strength is much greater than nominal strength. When you don't worry about that, you are lifting yourself out of fraction mechanics, which is a topic for a longer time, which is the 19th century problem. There, the same fascinating debate occurs. Do you use, so forget about flaws, forget about a notch, just a pristine sample, and you do, and it breaks. Let's say it be brittle material. The question again is you want to use an energy argument or a stress criteria to delineate the moment of fracture.
My feeling is that stress would be different at different points in the sample.
Oh, without question. Are you kidding? Without question. So
what you really have is different regions of the sample undergoing different.
along your line, this is exactly why when you measure nominal strength, it typically has a spread.
That's right.
And when the spread is very big, they actually immediately blame you must have a fracture mechanical problem. That the spread is a result of having different distributions of the size of the flaws. That's the logic that they use. But you obviously can imagine, even if this is a flaw-free problem, there could be a spread from sample to sample.
Yes.
Exactly. So this, so it's yeah. So people can easily get confused about what's happening. So yeah, I didn't say that the real message is the polymer just happened to be such that the crack is never so sharp. It's blunted enough for you to claim to be able to read the stress at the tip, resolving it optically. If you want me to do the same exercise for window glasses, I need a resolution of 1 nanometers, which I don't have. But since I have polymers, lucky at Akron, once you discover this problem, this formulation, of course, works for anything. In other words, do you follow me? You follow me, right? In other words, that P for polymer was 50 micron, 200 microns. That P, that characteristic length for window glasses is 1 nanometer. So you will be, of course, you will never establish this by studying window glasses. So it's sheer luck that the polymer is behaving this way. It's critical for you to be able to access tip stress because that's where you claim you know a sure way of your inherent strength and compare with nominal strength. The whole argument is, I hope nobody will debate with me that the tip stress at fracture is the inherent strength. I mean, you very easily say that because it's by the way, the stress, of course, is not a molecular parameter, right? It's already continuum average thing. So whatever you said is already being taken care of. It's statistical averaged out already. I know this is a long evening, but I enjoyed it. Yeah. Thank you. Thank you.